In this segment, we will begin describing what a binary search tree is and how it can efficiently implement the abstract data type we developed to solve the runway reservation problem. First off, a binary search tree is a binary tree. Keys and their associated data, if there is any, are stored in the vertices of the tree. The operations of the tree only depend on the values of the keys. So for this presentation, we only focus on the keys and assume there is no associated data. In other words, we treat the case of a set instead of the case of a map. Like set and map, the keys must have an ordering. We have a function which tells us when one key is less than another one. This ordering will determine the placement of the keys in the tree. Like a heap, a binary search tree has an invariant about the placement of keys in the tree. Consider any node in the tree and say that the key at this node is t. Then the key at the left child of this node must be less than t, and the key at the right child of this node must be greater than t. We call this the BST property, and this property should hold for every node in the tree. Since this property holds for every node in the tree, all the keys in the left subtree of a node are less than the key at that node, and all the keys in the right subtree of a node are larger than the key at that node. We represent this pictorially by this picture here. If the key at a node is x, then all keys in the left subtree are smaller than x, and all keys in the right subtree are larger than x. Here's our first question about the BST property. Where is the smallest key in a BST located? Well, to find the smallest key in a binary search tree, we can just start at the root and always go left. In this example, we would start at 7, then we go left to the node with key 3, and finally go left again to the node with key 1. And 1 is the smallest key in this tree. Likewise, to find the largest key in a BST, we can start at the root and always go right. In this example, we start at the root and go right to the node with key 10, go right again to the node with key 13, and right again to the node with key 20. And 20 is the largest key in this tree. Here is another question. If the keys are integers, what are the possible key values that could be stored in the node with the question mark? Again, assume that all keys are distinct. Well, the node with the question mark is the left child of the node with key 13, so the key there must be less than 13. On the other hand, this key is in the right subtree of the node with key 10. Thus, the question mark key must be larger than 10. Since it's larger than 10 and less than 13 and an integer, the only options are 11 and 12. So keys 11 and 12 could be placed at the question mark. Here we look at how we can start to implement a binary search tree. We have a node class on the left, as in a linked list, but now a node has two pointers, one to the left child and one to the right child. The node also stores a key value, and if we wanted to store some additional data associated with a key, we could add that to our node class as well. Here we stick with the simple case where we are just storing keys, which are ints. In the BST class, we have a pointer to the root node. This is again analogous to a linked list, where we maintained a pointer to the first node in the list. Finally, we have the methods of our abstract data type that we want to implement: insert, remove, contains, successor, and predecessor. We now move to discuss how to implement these methods. Here's a more detailed picture of a binary search tree drawing out the nodes. Each node has a pointer to its left child and its right child. The absence of a left or right child is represented with a null pointer. we see that for leaves of the tree, both the left and right variables are null pointers. Finally, the root variable points to the root node of the tree. And you can also see that each node holds its integer key value. The first method we will look at is the contains method to check if a given key is stored in the tree. This is one of the simplest methods and provides a template for the methods to come. The main idea is to begin at the root and walk our way down the tree, comparing the key we are looking for to keys at the current node we are at in the tree. We make crucial use of the BST property to tell us where in the tree to continue our search. Let us look at the example where we are searching for key 11. We first compare 11 to the key at the root. 11 is larger than 7, so if 11 is in the tree, it must be in the right subtree of the root. We thus continue our search at the right child of the root. This node has key 10, and again, 11 is larger, so we again move to the right child. Now we compare 11 and 13. 11 is smaller than 13, so we move to the left child of the node with key 13. And now finally, we've arrived at a node that has key 11. So we've found 11 in our binary search tree. Here we have some code to implement contains. We are looking for a node with key k. We define a temp variable, which is a pointer to a node, and initialize it to be the root. The temp variable will walk down the tree as we look for the key k. The condition in the while loop says that we keep walking down the tree so long as temp is not the null pointer and the key at the node pointed to by temp is not k, the value for which we are searching. How do we walk down the tree? We compare k to the key at the node pointed to by temp. If k is less than this key, then we move to temp's left child. Otherwise, we move to temp's right child. At the end of the while loop, either temp points to a node containing k, or it will be null pointer. If it's null pointer, that means that k is not in the tree. Here we're actually returning temp, but you could also modify this function just to return a Boolean value if the tree contains the key k or not, by returning whether or not temp is null pointer. Let's look at an example of how this code works on a key which is not in the tree. Let's say that we're looking for the key 6. So we initialize temp to be the root. Now it's not a null pointer, and the key at the root is 7, which is not equal to 6. So we enter the while loop. As 6 is less than 7, we update temp to point to the left child of the root. So now temp points to the left child of the root. Again, it's not equal to null pointer. And the key at this node is 3, which is again not equal to what we're looking for, which is 6. So we execute the body of the while loop again. This time, 6 is greater than 3, so we update temp to point to the right child. So now temp points to the node with key 5. Again, temp is not the null pointer, and 5 is not equal to the key we're looking for. So we execute the body of the while loop again. We compare 6 and 5, and 6 is greater than 5, so we update temp to point to the right child of the node containing 5. Now temp becomes null pointer. As temp is null pointer, the while loop terminates, and we return null pointer. This is the behavior we want in this version of contains, where the return value is a pointer to a node. Again, if we wanted to just return a Boolean value, we could just return whether or not temp is equal to null pointer at the end of the while loop. What is the complexity of this algorithm we have given for contains? Well, temp starts out at the root of the tree and walks down the tree. When the input key, k, is not in the tree, we have to walk all the way down until we reach a null pointer. In the worst case, we have to walk along the longest path from the root to a leaf in the tree, and so the number of iterations of the while loop will be the height of the tree. Thus, in the worst case, the algorithm will have to spend time that is at least proportional to h. Now let's think about the upper bound on the running time. To execute the body of the while loop just takes constant time. All we do is compare the input key to the key at the node pointed to by temp, and then update temp accordingly. Thus, we can also upper bound the running time by a constant factor times the height of the tree. So the overall worst case complexity of contains is theta of h. The function will always run in time order of h, and in the worst case, it will also take time at least a constant times h. This shows that the height of a binary search tree is very important to the running time of the contains algorithm. This will be a common theme for all the methods of the BST class, and we'll talk much more about the height of BSTs later. Now let's consider inserting a new key into the binary search tree. Inserting a new key is very similar to the example we have just seen of running contains on a key that is not present in the tree. Remember, we are treating the case where we don't have duplicate keys, so we only want to insert a key that is not already in the tree. Let's assume that we're in this case, where the key k we want to insert is not already in the tree. Again, this is something that we can check with the contains method we just saw. Insert begins exactly like searching for the key to be inserted in the tree. As the key k that we want to insert is not in the tree, we are going to end up at null pointer, as we just saw in the previous example of the contains method. This is where the key k is going to be inserted. We create a new node holding key k and update the null pointer to instead point to this new node. In particular, it's really important to remember that when a key is inserted, the node holding it will always be a leaf. Let's look at an example here where we want to insert the key 2. As in contains, we begin at the root and walk down the tree comparing 2 to the key at our current node. Now 2 is less than 7, so we move to the left child of the root. 2 is also less than 3, so we again move to the left child. Now 2 is greater than 1, so we move to the right child. We have reached a null pointer, so this is where we insert 2. So this is the picture of how the tree looks after inserting the key 2. Analyzing the complexity of insert is nearly identical to that of contains. We are always walking down the tree from the root to a null pointer. In the worst case, again, we have to walk along the longest path from the root to a leaf, so this will take time proportional to the height of the tree. Like in contains, at each step of the walk, we just have to do constant work. Thus, a constant times h, the height of the tree, will also be an upper bound on the running time. Overall, the worst case complexity is again theta of h. Now let's talk about the successor method. We have some input key x, and we want to output the minimum key in the tree that is larger than x. Again, let's assume that x is already in the tree. Successor is a bit more complicated than contains or insert, so let's build up to it slowly. Suppose that x is the key shown in the picture. Let's first think about where keys larger than x are located in this tree. Now, of course, x's right child and all descendants of x's right child will have keys larger than x. Again, we know this by the BST property. How about the node with key y? The node with key x is the left child of its parent, which has key y. Since it is the left child, this must mean that x is less than y. Also, everything in the right subtree of the node with key y has keys that are greater than y, and therefore also greater than x. Thus, all the nodes colored red in the picture have keys that are larger than x. Do we now know all the keys larger than x in the picture? What other nodes could have keys larger than x? Well, we're not done yet, because the node with key x is also in the left subtree of the root. Therefore, the key at the root, z, is also greater than x. Since the key y is also in the left subtree of the root, we know that z is greater than y as well. Further, everything in the right subtree of the root has keys that are larger than z and therefore also larger than x. Now we have identified all the nodes in the tree that are larger than x. They are all the nodes that are colored red in this picture. So now we know that all of z, y, and a are larger than x. But what is the relative ordering between z, y, and a? You can pause the video here and think about this for a second. The nodes with y and a are both in the left subtree of the root. Therefore, both y and a must be smaller than z. Further, a is in the left subtree of the node with y, so a must be smaller than y. Therefore, we know that a is less than y, which is less than z. So in this particular picture, a would be the successor of x. It is the smallest key in the tree that is larger than x. This example tells us that when looking for the successor of x, we should always look in the right subtree of x first. This brings us to case 1 of computing the successor of x. If the right child of x is not a null pointer, then the successor of x will be the smallest key in the right subtree of x. And we already know how to find the smallest key in this subtree. We just walk down the subtree, always going left, so long as the left child of the node that we are at is not null pointer. The key of the last node we reach on this walk, always going left, will be the successor of x. The remaining case in computing the successor of x is when the node with key x has no right child, as illustrated in this picture. In this example, the successor of x is the key y. We have already seen that y is less than z, and of course any key in the right subtree of y is bigger than y, and any key in the right subtree of z is bigger than z, which we already know is bigger than y. In general, when the node with key x has no right child, the successor of x will be the node where we last took a left turn on the path from the root to the node with x. We can implement this by modifying our contains algorithm, which recall starts at the root and walks down the tree comparing x with the key at the current node, and then moves to the left child or right child accordingly until it finds the node containing x. Now we can introduce a new variable which points to a node, and this variable might be called last left. Every time we go left on this walk from the root to x, we update last left to point to the node whose key is larger than x that results in us going left. Once we reach the node with key x, then last left will point to the node where we last took a left turn on this path from the root to the key holding x. Thus, if the node with key x has no right child, the key in the last left node will be the successor of x. The complexity of successor is very similar to contains and insert. We have to do at least as much work as in contains, as we first find x in the tree. In the worst case, we have to walk along the longest path from the root to a leaf, and so must take omega of h time, where h is the height of the tree. The algorithm also runs in order of h time. We just have constant overhead over contains and finding the node with key x in the tree and maintaining a pointer to the node where we last went left on the walk from the root to the node with x. The other operation we have to do is find the minimum key in the right subtree of the node with x, and this can also be done in order h time. Thus, overall, the worst case complexity of successor is theta of h. Finally, we come to removing a key from the tree. This algorithm is trickier than the ones we have seen so far. Let's start out with an easy case. Say that the node that we want to delete is a leaf. In this example, say we want to delete the node with key 5. The parent of the node with key 5 has key 3, and the node with key 5 is the right child of its parent. In this case, we can simply delete the node with key 5 and update the right child of its parent to be null pointer. So this is the picture of how the tree looks after key 5 has been removed and its parent updated so that its right child is null pointer. Now let's move up one step in complexity. Say that the node that we want to delete just has one child. In this example, say that we want to delete the node holding key 10. As this node only has one child, this child can simply replace the node with key 10 in the tree. In this case, the node with key 10 is the right child of its parent, and its parent is the root. So we update the right child of the root to instead point to the node with key 13. We can then delete the node with key 10. So this is a picture of the tree after the removal of key 10. Note that the binary search tree property is preserved in this removal. Key 13 becomes the right child of the root, but we already know that 13 is bigger than 7, the key at the root, since key 13 was already in the right subtree of the root. And also, we don't change anything in the subtree below the node with key 13. So the binary search tree property continues to hold in this subtree. Thus, overall, the tree still has the binary search tree property. Okay, now we get to the really interesting case, where the key to delete has both children. Let's say in this picture we want to remove the node with key 12. We again want to replace the node with key 12 by another node in the tree so that we preserve the binary search tree property. It is critical that we maintain this invariant in the tree. A first thought might be to replace the node with key 12 by one of its children. However, in this example, both children of the node with key 12 again have two children. So for example, if we were to replace 12 with key 17, we would have to figure out where we can put the left subtree of the node with key 17. And that is not very obvious. This difficulty suggests that it might be easier to replace the node with key 12 by another node that will preserve the BST property and such that this other node only has one child. So now the question becomes, what is a node that we can put in the position of key 12 that will preserve the BST property and such that this node only has one child? So a very good choice here is the successor of key 12. So in this picture, the successor of key 12 is key 15. By definition, the node with the successor will not have a left child. right? If it had a left child, then this key would not be the minimum key in the right subtree of the node with key 12. Moreover, we know that it is larger than everything in the left subtree of the node with key 12, since in particular it's a successor of 12, so it's bigger than 12. We also know that the successor is less than everything else in the right subtree of the node with key 12. Thus, if we replace key 12 by its successor, we will still preserve the BST property. Okay, now let's see in more detail how we can implement remove following this outline of replacing the key to delete with its successor. So when the node to remove has both children, let's again consider the example where we want to remove key 12. We first find its successor, in this case, the node with key 15. Then we remove this successor node from its original position by making the left child of its parent instead point to the right child of the successor node. So now our picture becomes like this. Okay, so we've replaced the left child of the node with key 17 with the right child of the successor node. Okay, so you can see that here. The parent of the successor has key 17, and we make its left child the right child of the successor node. So now our picture looks like this. The successor node has been excised from the tree, and its right child has taken its place. We now want to insert the successor node into the position of the node with key 12. Again, that's the key that we want to remove. So to do this, we update the right child of the parent of the node with key 12 to instead point to the successor node. And finally, we set the children of the successor node to point to the children of the node to remove. Okay, so doing that just inserts this key 15 into the position where the node that we want to remove was. Okay, so now we have linked in the successor of 12 into the position where 12 used to be. So after doing that, we're free to delete the node holding key 12 and free up its memory. So I should mention that there is a special case here that needs to be handled separately. And that is where the successor of the node to delete is its right child. So in this case, steps 2 and 3 have to be modified. In this case, you want the right child of the successor node to remain its right child. Finally, let's look at the complexity of the remove operation. We can essentially express the actions of the algorithm in terms of algorithms we have already seen. We first have to find the node with the key to delete. That's just like the contains algorithm. If this node has 2 children, then we have to find its successor. We've already seen how to do that. Apart from that, we just have a constant number of pointer updates to excise and insert nodes into their proper locations in the tree. So the complexity of remove is again theta h, where h is the height of the tree.